Welcome to what we call prime-square double gap, or violating the prime number theorem. Note it's in quotes. There is a strange quirk to be found in the gaps of the primes. Once we were able to prove the Riemann hypothesis, the math itself led to this experiment, predicting exactly what we're going to show you. And don't just consider these experiments, perform them for yourself. They're all a few lines of mathematical code, even though a lot of compute time. We only had available an ASUS netbook and a 5-year-old model at that. First, we reference the primes by their index on the positive naturals. Randomly choose 1,000 primes whose indexes range from 1 to 1,000,000. We choose this limit of 1,000,000 because Mathematica has a hard limit when calling prime pi, which is also the pi of x function. Having selected an m, calculate a gm, the gap, by calculating the next prime and taking the difference with the current prime. Divide this by the log of the prime and add it to an accumulator. Divide the finished number by 1,000 to find the average. Your result should be near 1. This is a direct result of the prime number theorem, or PNT, which says, on average, the gap between primes is about the log of the prime. Now repeat the experiment with a twist. Instead of measuring the gap at the local prime, measure the gap at that square. Or rather, where the square used to be, because obviously it's a composite. Choose m, calculate the prime, and find its square. Find the largest prime less than that square, and call it pk. Hence, because we're going as the square, this is why we have the limit to prime pi, because we're measuring from the index, but we're going to the prime square, which is going to grow very rapidly. So using 1.1 million will kill Mathematica. And add these things to an accumulator and take the average when finished. Since we perform our measurements at the square, the PN predicts our average should be 2. It will be 4. Making no difference if we divide by the natural log of our current prime, or pk, the nearest prime to our prime square. The result will still be twice as large as expected. Perform the same experiment, but reference the gaps to the left or to the right, and our expectations return to normal. That is, they return to the PNT. That is, there's a trivial recipe to sample the primes such that we statistically violate the PNT. Of course, there are many ways to perform the experiment. What we give next is a more systematic test that we performed. We calculated, or measured, the first 501 primes. We follow this with samples of 501 primes starting at 5,000, 10,000, through 140,000. Sampling our GK, as well as the gaps to the left and the right. The results are remarkable. The blue represents the gap at the square, our prime square double gap, divided by the logarithm. The red is to the left of that gap, and the yellow is to the right of that gap. And you can see this remarkable thing is the almost absence of variance. They're almost constants. The chart has 3 data sets, our normalized average gap at the square, and the same treatment to the left and the right. After 15,000 samples, our averages were basically 2 and 4. We also measured how frequently each gap was larger than the expected twice the log of the prime for each case. Our theory has no guidance for the prime square gap case because it's so specific. But in general, we predict a gap should be smaller than the expected mean, greater than 50% of the time. This is not a very specific prediction, so the result of this experiment came as a surprise. Once again, what appears to be almost constants with very little variance. The blue is our prime at the square, or gap at the square. The red is to the left and yellow is to the right. The probability that it was greater than the local average, the log of the prime, to the left and right was about just under 40%, and just about 80% for the gap at the square. Almost exactly twice. No reason to explain why it need be twice the probability, because we can't even explain. We can predict the blue, but we can't explain why it's the higher frequency. We know nothing about its frequency. In general, we expect a frequency a gap is larger than expected is less than 50%. And that is what we get for the randomly selected primes. It was about 38%. We call the data sets Fg as the frequency greater for the prime square, with Fg minus and plus being to the left and to the right. After 15,000 samples, we measured the following, and it's twice remarkable formula. Remember, we can only predict Fg and plus and minus to be less than 50%. The rest is for us to somehow still explain. We have unequivocal proof that the PMF, the probability mass function, for gaps at each location is top-heavy for gaps smaller than the mean. Unequivocal. Like we have the PMF, by the way. But that's all we've been able to prove. Just that it's top-heavy. It could be anything. Noise, a function of something. Our math gives us no guidance whatsoever. And here we have what seems to be constants. Who ordered that? Of course, we haven't really violated the PNT. That's impossible. The PNT is a fact of nature. What we found could best be considered a strange, aperiodic resonance, one which manifests itself translationally squared, that is, at the square. I don't know if there's anything else in nature like this. But however strange it is indeed easily measurable. A hint to deeper understanding of this quirk begins with a very close examination of the mechanics of prime sieving. For this, we built what we call the S-model. Next, you must accept as axiomatic the distribution of prime gaps, whatever the local or long-range forces there may be, are fundamentally random. To learn more, Google multiplication modulo n along the primorials, with its differences and variations applied to the study of the distributions of prime number gaps. Thank you for your time. We hope this was interesting.